St. Joseph College for Women Autonomous, Visakhapatnam. Welcome to St. Joseph's open web-based learning platform. So you learn for a soulful and enriching e-learning experience. This is Dr. G. Pankuma, Assistant Professor, Department of Physics, St. Joseph College for Women here, Visakhapatnam. First BSc second semester Physics, Unit 3, Mechanics of a Rigid Body and Continuous Media. Rigid body. A body which does not change its shape or size by the applying an external force. So such type of body is called rigid body. Next one is the constraint system. That means some kind of restrictions are imposed on the individual particles of the system. So such a type of systems are called constraint systems. Examples are the inertial and non-inertial frames. Angular position. If the particle P is in the plane, it requires two coordinates. That means position coordinate, position vector or an angle theta. Suppose the particle P is located at point A. If torque or an external force acting on it, the particle is moving in a circular path. That means A to B. So A to B from origin it makes some angle, that means theta. So if theta is increasing in anti-clockwise direction, so it is taken as a positive one. If theta is in clockwise direction, it is taken as a negative. So that means we are writing theta is equal to S by R. Angular velocity. Let P be a particle rotating in a clockwise direction at the time t1, that it can be written like P of t1. At the time t2, it is at P of t2. The angular positions are theta 1, theta 2. The angular displacement is given by theta 2 minus theta 1 is equal to d theta. During the time intervals, t2 minus t1 is equal to dt. So the average angular speed, that is omega, is given by omega is equal to d theta by dt. The instantaneous angular speed, that is delta theta by delta t, approaches to 0. Omega is equal to limit delta t tends to 0, delta theta by delta t is equal to d theta by dt. The units of the angular speed is radians per second or revolution of angular acceleration. That means the rate of change of angular velocity. So it is represented by the alpha. Alpha is equal to omega 2 minus omega 1 by t2 minus t1. So this can be written like this: delta omega by delta t. Suppose an instantaneous angular acceleration can be written like this: limit delta t tends to 0, delta omega by delta t is equal to d omega by dt. So units of the angular acceleration is radians per second square. Next topic, rotation with the constant acceleration. We know the kinematic equations like omega is equal to omega naught plus alpha t, theta is equal to omega naught t plus 1 by 2 alpha t square, omega square minus omega naught square is equal to 2 alpha theta, where omega naught is the initial angular velocity of the particle. First one, for angular acceleration, so we can write like this: omega naught into integral of 0 to omega d omega, that is equal to alpha dt. Alpha can be written like this: alpha is equal to d omega dt. d omega is equal to alpha dt. Omega minus omega naught is equal to alpha dt. Omega is equal to omega naught plus alpha t. Angular velocity. So we know that d theta by dt is equal to omega. So omega can be written like this: d theta by dt is equal to omega naught plus alpha t. So by rearranging the equation, d theta is equal to omega naught plus alpha t into dt. Angular velocity. d theta by dt is equal to omega naught plus alpha t. d theta is equal to omega naught plus alpha t into dt. So we are taking integrations on both sides. For theta, we are taking limitations from 0 to theta, and for time, we are taking limitations as 0 to t. So the above equation can be written like this: integral of 0 to theta d theta is equal to integral of 0 to t omega naught t dt plus integral of 0 to t alpha t dt. So after integration we are getting this equation theta is equal to omega naught t plus 1 by 2 alpha t square. Eliminating t, then t is equal to omega minus omega naught by alpha. After substituting t value in the above equation we are getting this equation theta is equal to omega naught into omega minus omega naught by alpha plus 1 by 2 alpha omega minus omega naught by alpha whole square. So after solving this equation we are getting omega square minus omega naught square is equal to 2 alpha theta. Relation between the linear and angular kinematics of the particle in a circular motion. Suppose if you are taking a particle P at a distance r from the center bone, with the rotation of the body, this particle moves in the circle of radius r. If in rotation through an angle theta, the particle travels along an arc, the distance s is given by s is equal to r theta. So theta is in radians. Differentiating the above equation with respect to time, so we can write like this: ds by dt is equal to r d theta by dt. ds by dt is equal to r omega. We know that omega is equal to d theta by dt. Differentiate the above equation, then we will get the relation between the magnitudes of the linear and angular velocities. du by dt is equal to r d omega by dt. That means a of t is equal to r alpha. Here a of t represents the tangential component of the acceleration, and then alpha represents the angular acceleration of the body. The force acting towards or away from the center is always radial and is represented by mv square by r. From this expression of the force, the radial component of the acceleration is v square by r. That means ar is equal to v square by r. We know that v is equal to r omega. I am substituting the value here. Ar is equal to r square omega square by r. So after that we get ar is equal to r omega square. Moment of inertia. A rotating body about an axis near a reference frame, the body resists any change in its rotational motion is called moment of inertia. The moment of inertia of a body about its axis of rotation is defined in the following steps. First one, the moment of inertia of a body about an axis is equal to the sum of the products of mass and the square of the distance from the axis of rotation. That is, I is equal to summation m r square. Second one, the kinetic energy of a rotating body with the angular velocity about an axis. So that is kV is equal to half I omega square. If omega is equal to 1, so I is equal to 2. Angular momentum of a rigid body. A rigid body rotating about an axis passing through a point O. The linear momentum of particle P of mass m is given by P is equal to mv. So next P is equal to m. We know B is equal to r omega, so that's why I am writing like this. P is equal to m r omega. That is equation 1. The moment of linear momentum above the axis of rotation, that means angular momentum, L is equal to P dot cross r. So L is equal to P means m r omega, so into r. So L is equal to m r square omega. The angular momentum L is the sum of the moments of all the particles of the body. That is, L is equal to summation m r square omega. We know that m r square is equal to I, that is the moment of inertia. So L is equal to I omega. Next one, torque tau. The force that tends to cause the rotation is called torque. Torque on a rigid body. Suppose the body rotates through a very small angle d theta in very small interval of time dt. During the time dt, the particle p moves from a position p of t to new position p of t plus dt along a circular arc of radius r. The distance covered by a particle p can be written like this: ds is equal to r dot d theta. The work done by the force of during the rotation is w is equal to f dot s. For small work done in a small interval of small displacement, so dw is equal to f dot ds. dw is equal to f dot ds into cos phi. Frame of reference. The motion of a body has meaningless. It is described with respect to some well-defined coordinate system. That coordinate system is known as a frame of reference. Next one, inertial frame of reference. A frame of reference is said to be inertial when bodies in this frame obeys Newton laws of inertia and other laws of Newtonian mechanics. In this frame, a body not acted upon by an external force, it is at rest or moves with a constant velocity. Example, non-inertial frames. The reference frames does not obey the Newtonian laws is simply known as a non-inertial frames. Example, rotational frame of reference. Example, let us consider the position of a pendulum bob in an accelerated car. When the car is at rest or in an uniform motion, the pendulum will be in the vertical position. But when the car is accelerating, it will be in equilibrium position in the position, making an angle theta with the vertical position. In this position, the interaction forces acting on the bob are tension along the thread and the force of gravity directed towards the earth. The resultant force of these two forces produce an acceleration to the bob in the direction of the acceleration of car. So as the bob is in equilibrium, the Newtonian sense prompts us to introduce another force, F inertial, in the direction opposite to the result. So that is ma plus F inertial is equal to 0. 50 force, a force that acts on all masses whose motion is described using a non-inertial frame of reference, such as rotating frame of reference. Consider two frames of references S and S dash, where S is OXYZ and S dash is OX dash Y dash and Z dash. Their origins remains same. The frame S dash is rotating with a constant angular velocity omega with respect to S frame in anti-clockwise direction. Consider a particle P of mass m having a position vector remains same in both frames S and S dash, but their components are different frames of reference. Consider when a particle P at rest with respect to S dash frame, the particle appears to be moving in a clockwise direction with a velocity v. So that is v is equal to omega cross r. Consider when the particle P in motion with respect to S frame, its velocity is v is equal to dr by dt. But with respect to S dash frame, its velocity is v dash is equal to v minus omega cross r. So v dash can be written like this: dr by dt of S dash frame is equal to v. So dr by dt of S frame minus omega cross r. The above equation in its terms of position vector r, which can be replaced by another vector r. Therefore, the operator form of the above equation can be written as d by dt of S dash is equal to d by dt of S frame minus omega into square open bracket. If we use the above equation for the velocity vectors S frame with respect to S dash frame, we can like this: d dv by dt of s is equal to dv by dt of s dash minus omega into v. Dr by dt of s is equal to dr by dt of s dash minus omega cross v dash into omega into r. So next dr by dt of s equal to dr by dt of s dash minus omega cross v dash means dr by dt of s dash into omega means d omega by dt of s dash into r plus omega v dash plus omega cross r. So the above equation is simply written like this: a is equal to a dash plus 2 into omega cross v dash plus omega into r. Multiplying the above equation with mass on both sides. So ma is equal to ma dash plus 2m omega into b dash plus m omega into r. So this can be, we know that ma is equal to f. So I want to write the above equation like this: f is equal to f dash plus fo, where fo is equal to 2m omega into v dash plus m omega into r. Fictitious force of two components are: first one is the Coriolis force and second one is the centrifugal force. Coriolis force means, by in the above equation, 2m omega into omega v dash. Centrifugal force means mr omega square. Centrifugal force is the particle at rest with respect to rotating frame of reference. Centrifugal force, that means the force acting away from the center of the mass of the body. So that is called centrifugal force. Example: a man sitting in a car which is moving on a curved road. Next one is the Coriolis force. It is a force that acts on a particle or a body in motion relative to rotating frame of reference. This force is proportional to angular velocity of rotating frame and v dash of the particle relative to it. So corresponding, there exists centrifugal acceleration and Coriolis acceleration. Effect of Coriolis force on a freely falling body. Consider a freely falling body whose initial velocity u is equal to 0. The height from which it falls is h at a time t to the surface of the earth at a latitude lambda. The body experiences Coriolis force with respect to the rotating frame of reference of the earth. Let us the angular velocity of the rotating frame be omega. Consider three axes, that means coordinate axis x, y, z at point A, where the body touches the ground. X axis along east, y axis along north, and z axis along the direction of freely falling body. The component of angular velocity omega along y axis will be omega cos lambda. The velocity of a freely falling body with respect to the rotating frame of reference v dash is similar to v. So we know the kinematic equation: v is equal to u plus at. So here initial velocity is 0, so that's why that equation comes to 0 plus gt. Therefore v dash is equal to gt. The height through which the body fall is s is equal to ut plus half at square. So here u is equal to 0, that's why h is equal to half gt square. So t is equal to, I am rearranging the equation, t is equal to root over 2h by z. As the body is in motion with respect to rotating frame of reference, there will be an effect of horizontal component of Coriolis force, but no effect of vertical component Coriolis force. The horizontal component of Coriolis force displaces the body through a small distance along the x-axis. F is equal to 2m omega into v dash. So a dash is equal to 2 omega into v dash. So Next one, a dash is equal to 2 omega cos lambda gt. So a means d square x by dt square, that is equal to 2 omega cos lambda gt. So after integration we are getting dx by dt is equal to 2 omega g cos lambda t square by 2 plus c1. c1 is the integration constant. When t is equal to 0, v is equal to 0, c1 is equal to 0, the above equation can be written like this: dx by dt is equal to 2 omega g cos lambda t square by 2. So after again we are integrating with respect to time. So x is equal to omega g cos lambda t cube by 3 plus c2. When t is equal to 0, x is equal to 0, therefore constant c2 is equal to 0. So x is equal to root over 899 g h 3 power by 2 omega cos lambda. So this represents the displacement along the x-axis. Special cases: for freely falling body at the equator, lambda is equal to 0. The displacement x is equal to root over 8 by 9 g h power 3 by 2 omega. It represents the maximum displacement. Second one, at the poles, lambda is equal to 90 degrees. So the displacement x is equal to 0. That means it represents 0 displacement. Next one, effect of centrifugal force on acceleration due to gravity. So magnitude is centripetal force is equal to m r omega square, that is equal to m capital R cos lambda omega square. So squaring on both sides, m g dash whole square is equal to mg whole square plus m r cos lambda omega square whole square. So after dividing the resultant equation, we are getting the final equation: g dash whole square is equal to g square minus 2g capital R cos square lambda omega square. G dash whole square is equal to, we are taking the common as a g square. So g square is a common term here. So 1 minus 2 r omega square by g cos square lambda. So final equation is g dash is equal to g minus r omega square cos square lambda. So this can be written by using binomial expansion. Due to centrifugal force, the acceleration due to gravity decreases compared to original gravity. Applications of Coriolis force: it is taken into an account to compute accurately trajectories of long range particles, long range projectiles and missiles. It is Coriolis force that produces counterclockwise circulation in the northern hemisphere, which affects course of winds. Spinning motion of earth is that cause equatorial bulge. This one is the very important topic here: symmetrical top or precision of top. A symmetrical body rotating about axis which is fixed at one point is called as a top. A top spinning about axis with angular velocity omega having a fixed point O. The axis of spinning top moves around vertical axis OZ swept out a cone. The axis of rotation of spinning top is called precision of top. The above figure represents the precision of the top. Let the center of mass of body be C with the position vector R. The weight of the top mg acts on top vertically downwards. So torque tau on the top will be tau is equal to r cross f, tau is equal to r cross mg, tau is equal to r mg sin theta. Angular momentum L max precisions after some time interval delta t with changing angular momentum. Thus, the new angular momentum will be L minus delta L. The angular velocity of precision top can be represented as omega p. Omega p is equal to delta theta by delta t. where delta theta be the angle turned by the angular momentum in a time interval delta t. So if you are taking uh, in the figure the triangle ABC, delta theta can be written like this: delta theta is equal to BC by AC. So here BC is equal to delta L by AC. So for the consideration of the AC value, so we are taking triangle AOC. Sin theta is equal to AC by OC. Sin theta is equal to AC by OC means L minus delta L. Here L minus delta L is similar to L, angular momentum. So sin theta is equal to AC by L. So by using the equation, AC can be written like this: AC is equal to L sin theta. So we are substituting value in delta theta. Delta theta is equal to delta L by L sin theta. So we know that omega p is equal to delta theta by delta t. I am substituting delta theta value in the equation 2. Omega p is equal to delta L by delta t into L sin theta. According to equation of motion of a rigid body, tau is equal to dl by dt. Omega p is equal to tau by L sin theta. So we know that omega p is equal to mgr by L. We know that L is equal to I omega. Here I represents the moment of inertia. Omega represents angular velocity of the top. Omega p is equal to mgr by I omega. From equations 4 and 5, the angular frictional velocity properties are: first one, omega p is inversely proportional to L of the spinning top, and second one, the frictional velocity is independent an angle theta. Third one, omega p is directly proportional to the mass of the body and inversely proportional to the mass of inertia of the body. By using this symmetrical top, we are able to understand the precession of equinoxes. The equatorial plane of the earth and the plane of its orbit round the sun are inclined each other at an angle 23.5 degrees. The two planes intersect at points A and B, known as vernal equinoxes, while the point B is known as autumnal equinoxes. The earth is in one complete round about an axis about the sun, crosses point A at about 21st March and point B at about 22nd September. The line joining the points A and B is known as line of equinoxes. At equinoxes, day and night are equal. Generally, we know that the earth is in a spherical shape. By using the equinoxes topic, so it is well known fact that the earth is not a perfect sphere but bulges out at the equator. And next, a gravitational force of attraction due to the sun and the moon on the equatorial bulge of the earth gives rise to a torque. As the two forces are not equal, this torque makes the axis of the earth to precess. As the earth acts like a top, its precessing axis describes a circular cone relative to the pole star assumed to be fixed. This precessional motion of the earth's axis causes a change in the direction of the line of equinoxes, which is called the precession of equinoxes. Stress. The magnitude of internal forces per unit area of the section is called as a stress. Stress is equal to F by A. Types of the stresses: normal stress and tangential or shearing stress. Normal stress means the component of the force perpendicular to the surface measured per unit area is called normal stress, that is equal to Fn by A. Tangential or shearing stress means the component of the force acting along the surface per unit area is called normal stress. that is equal to Ft by A. Next topic, strain. The relative change produced in the body under a system of forces is called as strain. Different type of strains are there. First one is the linear strain, second one volume strain, third one is the shear strain. Linear strain means the change in length per unit length of the body is called linear strain. Volume strain, the change in volume per unit volume is known as volume strain. Third one, in this case, an angular deformation, the strain is called as shearing strain. Elastic constants of isotropic solids and their relations. First one is the Young's modulus. It means the ratio of the longitudinal stress within elastic limit to the longitudinal strain is called as Young's modulus. That is equal to stress by strain, that is equal to F by A whole divided by S delta L by L, that is equal to FL by A S delta L. Next one is bulk modulus. Within the elastic limit, the ratio of normal stress to volume strain is called as bulk modulus of the material of the body. It is denoted by K. So K is equal to Fv by A S delta V. The reciprocal of bulk modulus is called as compressibility. Modulus of rigidity. When a body is a shear, then the ratio of tangential stress to the shearing strain is called as modulus of rigidity. It is denoted by eta. Eta is equal to F by A by theta. Next one, Poisson's ratio. Within elastic limit, the ratio of lateral strain to longitudinal strain is called as Poisson's ratio. It is denoted by sigma. Consider the length of the wire is L and diameter D. Let the wire be subjected to equal and opposite forces along its length. Suppose length increases to L plus S delta L while the diameter decreases to D minus S delta D. Sigma is equal to L into S delta D by D into S delta L. The strain is dimensionless quantity, so that Poisson's ratio has no dimensions. Next, beams. The structural member designed to support loads is known as a beam. Beams are usually long, straight, prismatic members designed according to the loads applied. When the loads are applied perpendicular to the axis of the beam, they produce only shear and bending. When the loads are not perpendicular, that means parallel to the axis of the beam, they produce axial forces in the beam. On the basis of the support, the beams can be classified as, first one, simple beam. So it is also called as a free supported beam. The beam is supported at the two ends. Therefore, a beam supported by a hinge or roller on smooth surface at the ends having one span is called as simple beam. So it is shown in this figure. Next one, overhanging beam. If one end of a beam is extended in the form of a cantilever beyond its support, this is known as overhanging beam. This is also shown in figure. Next one, continuous beam. A beam more than two supports is known as continuous beam. So that means the beam is supported by the n number of supporters. Next one, cantilever beam. A beam in which one end is built in a wall or any other support such that it cannot rotate or move transversely is known as cantilever beam. So this is shown in the below figure. Note, the main advantage of a hinged beam is that remains stable. The roller supported beam is that it can move easily towards left or right on account of expansion or contraction due to change in temperature. Next one, bending. The deformation of a material or structure when a force is applied cause it to curve. This phenomenon is particularly relevant in the study of mechanics of solids, where bending occurs when a load is applied to a beam or similar structure, resulting in a bending moment. The bending moment is a measure of the internal moment that resists the bending. So this shown is in the below figures. Types of bendings. First one is the uniform bending. That means where every element of the beam experiences bending with the same radius of curvature. This means that the bending moment applied to the beam is constant along its length, resulting in a uniform distribution of stress across the beam cross section. So this is shown in the below figure. Next one, non-uniform bending. When a beam is subjected to varying bending moments along its length, resulting in different radii of curvature for different sections of the beam. This type of bending is typically influenced by external loads that are not evenly distributed, leading to complex stress distribution within the material. So this is shown in this figure. Next one, load. Load means it refers the external forces or weights applied to a structure or material which can induce stress, strain and deformation. Loads can be characterized based on their nature and how they affect structures, particularly in the content of bending. So different type of loads. First one is the concentrated or point load. When a load acts on a beam over a very small length as compared to the total length of the beam, then the load is approximated to act at a point. The load is known as concentrated load or point load. Example, when a person stands on a beam, the load is regarded as a point load. So the below figure represents our definition. Uniformly distributed load. When the load is spread over the beam in such a manner that each unit length is loaded to the same extent, then this is known as uniformly distributed load. Example, consider a tank full of water up to the height h. Now the water load acting on the floor of the tank is known as uniformly distributed load. Next one is uniformly varying load. The load is spread over the beam in such a manner that it varies uniformly on unit length. Then this is known as uniformly varying load. This can be shown in the figure. Thank you.